Welcome! In this video, we'll explore LeetCode problem number 1647, minimum deletions to make character frequencies unique. This problem challenges us to manipulate character frequencies in a string to ensure uniqueness, with minimal deletions. We'll break it down step by step and uncover an efficient solution. Let's dive in. In this problem, you're given a string S made up entirely of lowercase English letters. The task is to determine the minimum number of deletions needed to ensure that every character in the string has a unique frequency. To clarify, a frequency is simply the number of times a character appears in the string. You're allowed to delete any character from the string as part of an operation, and the goal is to achieve this condition of unique frequencies with as few deletions as possible. For example, if two characters have the same frequency, you might need to delete some occurrences of one of them until all frequencies are distinct. The input is a single string, which can be as short as one character or as long as 100,000 characters. The output will be an integer representing the minimum number of deletions required to meet the unique frequency condition. Let's start with an example to understand this better. Suppose the input string is s equals ob. First, we calculate the frequencies of each character in the string. Here, a appears 2 times, and b appears 1 time. Since all the character frequencies are already unique, A has a frequency of 2 and B has a frequency of 1, there's no need for any deletions. As a result, the output for this example is 0. Now, consider a different string, s equals abc. In this case, the character frequencies are as follows: A appears 3 times, B appears 3 times, and C appears 2 times. Notice that the frequencies of A and B are not unique since they both have a frequency of 3. This means some deletions will be necessary to make all frequencies distinct. For the string s equals abc, we need to modify the frequencies 3, 3, and 2 to make them unique. One way to do this is by reducing the frequency of A from 3 to 2, which involves deleting one occurrence of A. Alternatively, we could reduce the frequency of B to 2 by deleting one B. After this step, the frequencies become 2, 2, and 2. However, these frequencies are still not unique because all three values are the same. To resolve this, we can reduce the frequency of C from 2 to 1, which requires deleting one occurrence of C. Now, the final frequencies are 2, 2, and 1, and they are all distinct. The total number of deletions required is 2, 1 to reduce A or B and 1 to reduce C. This satisfies the condition of having unique frequencies. Now, let's examine another example with the string s equals cbap. The character frequencies here are: A appears 3 times, B appears 2 times, C appears 2 times, and E appears 1 time. The frequencies 3, 2, 2, and 1 are not unique, so deletions are needed. First, we can reduce the frequency of A from 3 to 2 by deleting one A. This adjustment changes the frequencies to 2, 2, 2, and 1. However, we still have a problem because 3 characters now have the same frequency of 2. To fix this, we reduce the frequency of one of these characters, such as B, from 2 to 1 by deleting one B. Now, the final frequencies are 2, 2, 1, and 1, and all frequencies are unique. In total, we needed 2 deletions, 1 to reduce A and 1 to reduce B. This example demonstrates how we can iteratively adjust frequencies to achieve the minimum deletions required. The constraints ensure that the solution must be efficient, and a greedy approach can help us systematically reduce frequencies while minimizing deletions. To solve the problem of finding the minimum deletions required to make character frequencies unique, we first considered a brute force approach. The core idea here is to compute the frequency of each character in the string and then systematically try all possible combinations of deletions. This means, for every collision in character frequencies, we explored different ways to remove characters until all the frequencies are unique. While this method is conceptually straightforward, it involves generating and checking all potential combinations, which grows exponentially as the input size increases. This makes the brute force approach impractical for larger strings. While it helps us grasp the problem and its constraints, its computational inefficiency makes it unsuitable for real-world applications where performance is critical. Instead, we turn to a more optimized solution, the greedy algorithm. Here, the key insight is to focus on resolving frequency collisions efficiently. When multiple characters share the same frequency, we aim to reduce these frequencies systematically, starting with the highest values. The steps are clear. First, compute the frequency of each character in the string. Then, use a set or similar structure to track which frequencies have already been used. For each frequency, sorted in descending order, we check if it's already in use. If so, we reduce the frequency through deletions until it reaches an unused value or becomes 0. At each step, we count the total deletions required. The greedy approach ensures that we resolve collisions with minimal operations. Its time complexity is dominated by the sorting step, which is O, n log n, where n is the number of unique characters, making it efficient and scalable for larger inputs. Given the options, we chose the greedy algorithm as the most effective strategy for this problem. While the brute force approach is conceptually correct, it becomes computationally infeasible for larger inputs due to its exponential time complexity. The greedy algorithm, on the other hand, strikes a balance between efficiency and ease of implementation. By focusing on frequency collisions and resolving them iteratively, it ensures that no two frequencies are the same while minimizing the number of deletions. The key insight here is that the problem can be simplified to managing these collisions by reducing higher frequencies to smaller, unused values. This systematic approach avoids unnecessary computation and guarantees correctness. The realization that we can focus on reducing only the conflicting frequencies, rather than exhaustively testing all possibilities, is what makes this strategy so powerful. When comparing the different approaches, the trade-offs become clear. The brute force method, while theoretically valid, is far too slow for practical use and only suitable for very small inputs or theoretical exploration. The greedy algorithm provides an efficient and straightforward solution, balancing simplicity and performance. An alternative approach, such as using a heap to manage frequencies dynamically, could also work, but it introduces additional complexity without significant benefits over the greedy method. Ultimately, the greedy algorithm is the optimal choice for this problem, offering clarity, efficiency, and scalability, making it well-suited for both small and large input sizes. In this problem, we need to determine the minimum number of deletions required to make the frequencies of all characters in a string unique. Let's consider the example where the string s is abc. The frequency of each character is as follows: A appears 3 times, B appears 3 times, and C appears 2 times, so the frequency map is A, 3, B, 3, C, 2. To make the frequencies unique, we can delete 1B, reducing its frequency from 3 to 2, and then delete 1C, reducing its frequency from 2 to 1. As a result, we end up with the frequencies A, 3, B, 2, C, 1, which are now unique. In total, 2 deletions were needed. To solve this problem, the first step is to count the frequency of each character using a hash map. This gives us an organized way to identify characters with duplicate frequencies. From there, we need to determine how to resolve conflicts among these frequencies systematically. Once we have the character frequencies, the next step is to make them unique. To achieve this, we use a set to keep track of the frequencies that have already been used. For each frequency in the hash map, we check if the frequency is already in the set. If it is, we simulate a deletion by decrementing the frequency by 1 and increasing the deletion counter. We continue reducing the frequency until it becomes either unique or 0. Once the frequency is unique, we add it to the set of used frequencies. This ensures that no two characters share the same frequency. After processing all the characters in the map, the deletion counter will represent the total number of deletions required to make the frequencies unique. This approach resolves conflicts in a controlled and efficient manner, ensuring that the problem constraints are met. The key idea behind this algorithm is its greedy approach. At every step, we resolve conflicts by reducing frequencies in a way that minimizes the number of deletions. This strategy prevents cascading conflicts, where unresolved issues at one step might create new problems later. By leveraging a hash map to store character frequencies and a set to track used frequencies, the solution achieves high efficiency, with a time complexity of O, n plus k. Here, n is the length of the string, and k is the number of unique characters. For edge cases, if the string is empty, no deletions are needed, so the output is 0. If all characters are already unique, no changes are necessary. On the other hand, if all characters are the same, we reduce the frequency down to 1 by making deletions. The main data structures used include a hash map for frequency counting, a set for tracking used frequencies, and a simple integer counter to track deletions, all of which operate efficiently. To summarize the complexity of this solution, the time complexity is O, n plus k. Counting character frequencies takes O, n, where n is the string length, and resolving conflicts involves processing up to k unique characters, making the algorithm highly scalable. The space complexity is O, k, as the hash map and set used are proportional to the number of unique characters. Let's walk through an example to see the algorithm in action. For the input string AAB, the initial character frequencies are A, 3, B, 3, C, 2. The frequency of it is 3, which is added to the set without conflict. The frequency of B is also 3, but since 3 is already in the set, we reduce B to 2 and add it to the set. Similarly, the frequency of C is 2, which conflicts again, so we reduce C to 1 and add it to the set. In total, 2 deletions are made, one B and one C. The result is that all frequencies are unique, and the output is 2, representing the minimum deletions required. This ensures the solution is both optimal and efficient. This solution efficiently determines the minimum deletions required to make all character frequencies in a string unique. Here's a detailed explanation of the approach. 1. Character frequency count. First, we calculate the frequency of each character in the string using Python's collections counter. This provides a dictionary-like structure where each key is a character, and the value is its frequency. 2. Tracking used frequencies. To ensure all frequencies are unique, we use a set called used_frequencies. This set will store all the frequencies that have already been assigned. 3. Iterate over frequencies, for each character and its frequency. If the current frequency, count, already exists in used_frequencies, we repeatedly decrement the frequency, count-1, until it either becomes unique or reaches 0. Each decrement represents a deletion, so we increment the deletions counter accordingly. If the frequency becomes unique, greater than 0, we add it to the used_frequencies set. For edge cases, this approach naturally handles edge cases, such as strings with all unique characters, no deletions needed. Strings with repeated characters requiring many deletions to ensure uniqueness. Empty strings, which result in 0 deletions. 5. Return result. Finally, the deletions counter is returned as the result, representing the minimum deletions required. This solution is efficient, with a time complexity of O, n plus k squared, where n is the length of the string and k is the number of unique characters. The space complexity is O, k, as we use a set to store unique frequencies. Here, we start by importing the necessary packages and defining our solution class. The method minDeletions takes a string s as input. The first step is to count the frequency of each character in the string, which we do using an integer array char frequencies of size 26, corresponding to the 26 lowercase English letters. For each character in the string, we increment the count in the array at the index determined by c a dot. This gives us the frequency of each character in the input string. Next, we initialize a hash set called used frequencies to keep track of frequencies that are already used, ensuring they are unique as we process the string. We also initialize a variable deletions to 0, which will store the total number of deletions required. Then, for every frequency in the char frequencies array, we check if it's already present in the used frequencies set. If it is, we decrement the frequency until it either becomes unique or reaches 0, and we increment the deletions counter for each decrement. Once we achieve a unique frequency greater than 0, we add it to the used frequencies set, ensuring that it won't cause any conflicts moving forward. Finally, once we've processed all character frequencies, we return the total number of deletions stored in the deletions variable. This value represents the minimum number of deletions required to make all character frequencies unique. The logic ensures that we efficiently handle the frequency constraints using the set, and by iterating through the array just once, we maintain a time complexity of O, n, where n is the length of the string. This makes the solution both clean and optimal for the problem. To solve this problem, let's work through an example where the input string s is ABC. First, we analyze the input. The string has 6 characters, and we can see that each character appears twice. Next, we calculate the frequency of each character using a counter, which gives us a 2, B, 2, C, 2. Now, we initialize two things, a set called used_frequencies to track the frequencies we've already used, and a variable deletions set to 0 to count how many deletions we make. Then, we process each character one by one. Starting with a, which has a count of 2, we check if 2 is in used_frequencies. Since it's not, we add 2 to the set, and no deletions are needed at this step. Next, we move to b, which also has a count of 2. This time, 2 is already in used_frequencies, so we reduce the count of b to 1 and increment the deletions counter by 1. Now, used_frequencies contains both 2 and 1. For c, which also has a count of 2, we find that 2 is still in used_frequencies, so we reduce its count to 1 and increment deletions by 1 again. However, 1 is also in used_frequencies, so we reduce the count of c to 0 and increment deletions once more. At this point, all frequencies are unique, and we've made 3 deletions in total. We return deletions equals 3 as the final output for this example. Now, let's work through another example where the input string s is abcapped. First, we analyze the input. The string has 6 characters, and each character appears twice. Using a counter, we calculate the frequencies as a, 2, b, 2, c, 2. We then initialize used_frequencies as an empty set and deletions as 0. Starting with a, which has a count of 2, we check if 2 is in used_frequencies. Since it's not, we add 2 to the set, and no deletions are needed at this step. For b, which also has a count of 2, 2 is already in used_frequencies. So, we reduce the count of b to 1 and increment deletions by 1. Now, used_frequencies contains 2 and 1. For c, which also has a count of 2, we again find that 2 is in used_frequencies, so we reduce its count to 1 and increment deletions by 1. However, 1 is also in used_frequencies, so we reduce the count of c to 0 and increment deletions once more. At this point, all frequencies are unique, and we've made 3 deletions in total. We return deletions equals 3 as the final output for this example. Let's take a look at another example where the input string s is cbap. First, we analyze the input. The string has 8 characters, and we calculate the frequencies as c2, e1, a3, b2 using a counter. We initialize used_frequencies as an empty set and deletions as 0. Starting with c, which has a count of 2, we find that 2 is not in used_frequencies, so we add 2 to the set, and no deletions are needed at this step. For e, which has a count of 1, we check if 1 is in used_frequencies. Since it's not, we add 1 to the set without making any deletions. Next, for a, which has a count of 3, we find that 3 is not in used_frequencies, so we add 3 to the set, and again, no deletions are needed. Now for b, which has a count of 2, we see that 2 is already in used_frequencies. We reduce the count of b to 1 and increment deletions by 1. However, 1 is also in used_frequencies, so we reduce the count of b to 0 and increment deletions by 1 again. At this point, all character frequencies are unique, and we've made 2 deletions in total. The final output for this example is deletions equals 2. This demonstrates how the algorithm ensures all frequencies are unique while minimizing the number of deletions required. To understand the time complexity of this solution, we break it down into 3 main steps. First, the character frequencies are counted using Python's counter, which processes the input string s in n time, where n is the length of the string. This is because it iterates through each character in the string once. Next, we iterate over the frequency dictionary, which contains at most 26 entries since there are only 26 lowercase English letters. This step has a constant time complexity, O1, as the number of entries does not grow with the size of the input. Finally, we adjust frequencies to ensure they are unique. For a given frequency, the inner while loop may reduce the frequency from n all the way to 0 in the worst case. However, since there are at most 26 characters, the total work done in this step is bounded by O(n). This ensures that even the most computationally intensive part of the algorithm remains efficient. When we combine these steps, the overall time complexity of the algorithm is determined by the O(n) operations required to count frequencies and adjust them. Therefore, the total time complexity is O(n). Now, for space complexity first, consider the space used by the frequency dictionary frequency. Since there are at most 26 lowercase English letters, the dictionary can hold a maximum of 26 key-value pairs, making its space requirement 1. Next, we have the used underscore frequencies set, which stores the unique frequencies of characters. In the worst case, if all characters in the input string have distinct frequencies, this set will grow to a size of n. Lastly, the algorithm uses a constant amount of additional space for variables like deletions and loop counters, which adds 1 space. Combining these, the total space complexity of the solution is n. To analyze the best, average, and worst case scenarios for this algorithm, we start with the best case. Here, all characters already have unique frequencies, so the while loop does not need to make any adjustments. In this scenario, the algorithm processes the string in n time. For the average case, some characters require their frequencies to be adjusted, and the while loop iterates a few times for some of these characters. However, the total number of operations still remains bounded by n. In the worst case scenario, all characters have the same frequency, such as when the input string consists of repeated instances of a single character. In this case, the while loop runs n times for the character, but since there are at most 26 unique characters, the total work across all characters remains n. This ensures that the algorithm is efficient across all cases. To highlight the efficiency of this solution, let's compare it to a brute force approach. A brute force method would involve trying all possible deletions to make frequencies unique. This would require generating all subsets of characters and checking their frequencies, leading to an exponential time complexity of 2 to the power of n, due to the combinatorial explosion of subset generation. In contrast, the given solution uses a greedy approach that operates in n time, making it exponentially faster and more practical for large inputs. To confirm the n time complexity mathematically, we sum up the runtimes of each step. Counting frequencies takes n, iterating through the frequency dictionary takes 1, and adjusting frequencies is n in total across all characters. Adding these together, the runtime is n. Similarly, the space complexity is dominated by the used underscore frequencies set, which requires n space in the worst case. Therefore, both time and space complexities are confirmed to be n. When tackling this problem, there are several common mistakes to watch out for. First, some users skip sorting the frequency counts before resolving conflicts. This is problematic because resolving conflicts without sorting often leads to inefficient or incorrect solutions. Sorting in descending order ensures you're addressing the largest frequencies first, which minimizes the number of deletions needed. Another frequent mistake is deleting characters directly from the string, rather than adjusting the frequency counts. The goal is to manage the counts themselves, not manipulate the input string, as modifying the string introduces unnecessary complexity and potential errors. Finally, there's the issue of not accounting for empty frequencies. If a frequency is reduced to 0, it can still create conflicts with other characters if not handled properly. Overlooking this edge case can lead to unexpected results, as 0 frequency slots should not interfere with others in the resolution process. Additionally, some solutions suffer from inefficiency due to the use of nested loops or brute force techniques for resolving frequency conflicts. These approaches often result in high time complexity, such as n squared, making them impractical for larger inputs. Another issue is skipping edge cases during testing. For example, strings with all identical characters, like AAA, or strings with no conflicts, such as ABC, are often overlooked. Missing these edge cases can cause your solution to fail during interviews or on hidden test cases in platforms like LeetCode. It's essential to account for these scenarios to ensure your solution is robust and reliable. Now, let's focus on some key insights relevant for interviews. A critical aspect of this problem is resolving frequency conflicts in descending order. Sorting frequencies ensures that the largest conflicts are addressed first, which helps minimize cascading deletions. This approach is a classic example of the greedy algorithm pattern, where making locally optimal choices, like resolving the largest frequency conflicts first, leads to a globally optimal solution. Interviewers may also ask you to compare your approach to alternatives, such as using a priority queue instead of sorting. This discussion can involve trade-offs in complexity and implementation details. Be prepared to highlight edge cases, like strings with all unique characters, all identical characters, or very large inputs up to the size limit of 10 to the power of 5. Demonstrating how your solution efficiently handles these scenarios can leave a strong impression. This problem shares similarities with several other LeetCode problems, making it a great opportunity to connect concepts. For instance, LeetCode 451, Sort Characters by Frequency, involves similar frequency logic but focuses on sorting characters rather than resolving conflicts. LeetCode 767, Reorganize String, requires rearranging characters to meet specific constraints, which also involves frequency manipulation. Another related problem is LeetCode 406, Queue Reconstruction by Height, which is a greedy problem that revolves around sorting and resolving conflicts. Finally, LeetCode 621, Task Scheduler, uses frequency counts to minimize idle time, following a similar approach to handling character frequencies effectively. Studying these problems can help you recognize patterns and apply similar strategies across different scenarios. Finally, let's examine some alternative approaches to solving this problem. One option is the priority queue approach, where a max heap is used to always resolve the highest frequency first. After processing, you push the reduced frequency back into the queue if it's still non-zero. While slightly more complex to implement, this approach avoids the need for presorting and achieves a similar time complexity of O(n log n). Another method involves using a hash map to track frequency counts and a set to record used frequencies. Here, you iteratively adjust the frequencies to avoid conflicts. This approach is intuitive and beginner-friendly but may involve additional overhead due to repeated set operations, maintaining a complexity of approximately O(n log n). Lastly, there's the brute force approach, where all possible deletions are tried for each conflict. While this is highly inefficient, with a complexity of O(n squared, it can be useful for debugging smaller test cases. Understanding these alternatives can help you adapt your solution to different constraints and trade-offs. Great job! Today, we tackled a challenging string manipulation problem using a greedy and efficient approach. Remember, mastering problems like these strengthens your algorithmic thinking. Be sure to practice similar questions to solidify your understanding. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!